One more thing. Papen is the right way to pronounce your name,
Yeah,
right?
that's a great question coming from you, Stefan. If I was still back in Germany, it would have been von Papen.
Right. Okay. Good.
So I can
So we do
actually,
it the American way,
yeah.
right?
So
So
yeah, so that's that got messed up as we came over.
okay, I got it. It's my great pleasure to introduce George Papen. So George is a professor of electrical and computer engineering department at University of California, San Diego. He's a leading researcher in systems applications of optics in computing and communication, and currently mainly focusing on optical circuit switch data center networks. He co-authored seminal works on reconfigurable networks, including RotorNet. So in 2020, he was also awarded with the IEEE Photonics Society Engineering Achievement Award. So thanks a lot, George, for being here. And yeah, looking forward to your answers.
Well, thank you very much for inviting me. It's a real pleasure.
Hi, George. Okay, so maybe we'll start by you telling us a bit about your background and how you become a researcher in the area of reconfigurable data centers networks.
Sure. I've been doing this a pretty long time. I started doing optical interconnects within digital systems in the early 1990s, believe it or not, and continue to do that. There's always been a struggle about pushing optics closer and closer to systems, and that's been a slow evolution. By the mid-2000s, we had a large research center interested in integrated access networks. And as part of that, there was an effort within that center by UCSD researchers, Amin Vedat, myself, Shia Feynman, to ask the question, could optical circuit switching be beneficial to data centers? There was work prior to that for high performance computing, but that center and getting together systems people like Amin and physical optics people like myself, Joe Ford and Shia, led to the first demonstration of using OCS for data center applications. We were fortunate that we had a large influx of money from NSF that allowed us to buy 72 servers. At that time, George Porter was working with Amin, and he actually assembled what we eventually called the seed test bed, 72 servers, and then a optical circuit switch that was actually at UCSD as part of another project. And that led to Helios, and that kind of kick-started all of the work on optical circuit switching within data centers at UCSD.
Very nice. Can you please describe us the main technologies that enable the optical circuit switches that are used in this reconfigurable data centers, and do different like OCS technologies also come with like different trade-offs, like in terms of performance or reconfiguration speed, energy consumption, cost, etc.?
Yeah, so that's a great question, because most of the time when people talk about optical circuit switching, they tend to focus on the actual optical switch itself. So I'll do that. But in order to get data from from the ingress port to the egress port through the network, through the switch, you actually need transceivers and some coordination of the data, because these switches basically are effectively an optical crossbar with none of the buffering that you would see in a standard electrical switch.
Right.
So literally make physical connections from input to output ports. They can be classified in many ways. One of the biggest classifications is space switched versus wavelength switch. So in space switching, you literally change the spatial configuration, and the dominant technologies for that are MEMS, microelectrical mechanical systems.
Yeah.
Those have been around for 20 years. There's another technology that has been commercialized based off of piezoelectrics, and that's Pilatus, which is now a subsidiary of a Swiss company. And those are the, and those I would call space-switched three-dimensional switches. There's also space-switched two-dimensional switches that are planar technologies, because it has been long believed that you could lithographically define these and drive the cost down. There's many variants of that. I think one of the most interesting one is the one that Ming Wu has championed, which is actually putting MEMS on a planar structure to be able to produce that. But there's also Mach Zenders. There were micro rings. So once we get into the planar switches, there's a whole list of technologies that have been proposed and demonstrated experimentally. One economic aspect, is the space switches. The 3D space switches have been around for 20 years. And one of the most costly components is what's called the fiber collimator array. So these are switches that have to have inputs with fibers and output with fibers. And the fibers have to actually interface with the guts of the switch. So these fiber collimator arrays are a separate ecosystem. They're commercially available. When we make our switches, we can actually buy them, even as a university. And that has been, in some sense, a limit of the planar switches, because trying to build these switches and attach all the fibers that you need to the planar switch, to the best of my knowledge right now, there isn't a separate ecosystem for that. So this has been a real barrier for the implementation and the commercialization of the planar switches, is because while we can go out and buy these fiber collimator arrays, as I said, you have to, if you're going to build a 128 by 128 switch, you need 256 separate fibers that have to be attached to that. And that has been a barrier so far. So that is space versus, that's space 3D and 2D. Then there's also wavelength switching. Wavelength switching is commercialized. It's used in wide area networks. These things are called reconfigurable add drops, commonly called ROADMs. And then the guts of those use what's called a wavelength selective switch. So these are commercialized. They make a lot of them. They're in all wide area networks. Again, that technology that's been commercialized is a three-dimensional technology for these wavelength selective switches. And because of how they work, they tend to basically take the input and spread it out. In other words, split it, and then switch it and then put it back together again. They tend to be lossy. Okay, so we built a wavelength selective switched architecture right after Helios. It was called Mordia. And because of that, we had to use optical amplification. And while that can be justified in wide area networks, because you can amortize across many users, at least as we speak in 2024, to the best of my knowledge, that has not been commercialized to the point that it's widely used in data centers, because of the cost of actually, well, first the cost of the wavelength selective switch, and then the biggest thing is that you tend to have to optically amplify. That's true for both the 3D and many of the proposed 2D technologies using wavelength selectives, using wavelength. The other issue from a physical optics standpoint is that the space switching doesn't care about the modulation rate or the modulation format, because literally on most of these devices, you're just bouncing off of mirrors, and the mirror doesn't care how fast the data is being changed or in what format it is. For the wavelength switches, that's not necessarily the case, because the wavelength splitting elements tend to be fixed bandwidth. They don't have to be, but they tend to be. And they are, if you will, not as transparent to the data rate and or modulation format as space switching, okay? And to make them more transparent, again, you can do this, and it's actually done in the wide area network. This is called elastic grid or flexible grid, WSSs. It just incurs more cost. So I think the net total of the question that you're asking is that you have space switching, wavelength switching, you have 2D, you have 3D. But at least as we stand here in 2024, to the best of my knowledge, all commercial optical switches are three-dimensional. All demonstrated switches in data centers to this point are space switched. And wavelength switches do exist, and they have been commercialized for the wide area network. But again, I have not seen a commercialized version of a wavelength switch for data centers. So that's kind of a broad brush picture of the technologies for switching. Now for transceivers, we'll tend to, I apologize. For switching, excuse me, for transceivers, you have to have transceivers be compatible with the optical switch. And the biggest issue is that for all these switches, regardless of whether they're wavelength or space switch, you literally break the optical connection and you reestablish it. And that does not happen in a standard data center. In a standard data center with electrical switches, the transceivers are always on. So even if you're not sending data, you're sending idles. You're always sending transitions. So once the transceiver, quote unquote, locks, which means it establishes that it's found where the clock edges are and so on, it never loses lock unless something breaks. Okay.
So
for all optical switching technologies, you're constantly breaking and reestablishing optical links. And that means that the transceivers have to be able to reacquire the optical data stream after a switching event. Now for slow switching, like, if you're switching on, I don't know, pick a number, tens of milliseconds, that tends not to be as much of an issue. But for some of these very sophisticated modulation formats, just the initialization of the transceivers, how long they take to find everything that they need to find, is not an insignificant time. Okay, that turns out to be equally as important as a switch, because if you can't acquire the signal, you don't have it. Okay, so it's a combination of both switch technology and transceiver technology, and you need to have both. And you can't, and a lot of the research switch technology is using relatively customized or one-off research devices. But reacquiring the data is going to be, a challenge as we try to push optical transceiver technology faster and faster. I mean, Sirius did I mean, a good example of that is Sirius did a very, very clever thing where they basically cached the phase of the clock, right? If you're familiar with their work, to be able to reestablish it at a nanosecond time.
Right.
But this is, but that kind of technology, as we speak, has not been commercialized.
Okay, so what you say essentially is that this is a disadvantage, what we call a latency tax. For when we reconfigure, we have to spend some time. But what are the advantages of using reconfigurable optical data center, especially when you compare it to data centers that are based on electrical packet switching?
So as I said before, so let's talk about the advantages as have been published. Okay, so the biggest advantage, and again, I think I'll probably defer to Avin since it's running in production at Google, but the biggest advantage for the DCN is the fact that it is truly agnostic to data rate and modulation format. So Google has publicly stated that I think they're on their 5th generation of transceiver technology using the same optical switching technology. That's impossible for an electrical packet switch. An electrical packet switch is designed for a data rate. So, but we've gone from 40G to 100G to 200G to 400G, and 800G is on the horizon. And every single time you change the data rate, you have to change the optical switch. Excuse me, the electrical switch. That does not happen for a type of switch. These space switched, 3D switches are truly transparent over an enormous bandwidth. Okay, And that has allowed the switch to become part of infrastructure, and you're not swapping it out on the same schedule that you are, your servers and so on. So it becomes part of the infrastructure. So that's a huge advantage in terms of just running your infrastructure. And Google has several numbers about how big that advantage is. So that's one thing. The second thing is, while it is true that you are bounded either by the transceiver locking time or the switching time, you're not bounded by queuing delay. And more importantly, you are not bounded by the randomness that queuing delay gives you. So you now make a trade that, as I said, there's no buffering in the switch. So once the data leaves the egress port, you have deterministic time of flight to the ingress port. And that is not generally true in an electrical switch unless it's completely unloaded, because the electrical switch is actually trying to take advantage of that and have a little bit of queuing so that it can run efficiently. So the big advantage is, if you can take advantage of them, is they're deterministic. They don't care, at least for the switches that we're interested in, they don't care about the modulation format or the data rate. And those tend to be significant advantages. With respect to machine learning, the two advantages that have been published are, one, that you can use the switches to swap out bad compute blocks, so that you can basically have greater availability of these large machine learning resources. And I think a much more interesting one is that you can use the switches to change, and I need to be careful here, the topology remains the same for these superpods. These still are torus topologies, but you can use the switches to change the dimensions of the torus. And by using the switches to change the dimensions of the torus, you can better match the dimensions of the torus to the dimensions of the machine learning model. And that turns out to be an extremely interesting and beneficial feature of optical circuit switching for machine learning, at least in the context that Google uses it, because they built torus type architectures. So again, for the DCN, one of the huge advantages was backward, the ability to be able to go through multiple generations of transceiver technology. For machine learning, it was availability and the ability to shape the size of the dimensions of the torus to the machine learning model. And all of those in two different contexts, I think, are significant reasons why it's being used as we speak.
So you see machine learning as a particularly well-suited workload here for this kind of applications, or?
Yeah, that remains to be seen. I think the issue is that certainly with how it's being used today, I think it will be continued to be used for exactly those two reasons. Whether or not there are other benefits of optical circuit switching for machine learning, besides the ones that have already been discussed, I think that's an area of future exploration. But given that this is the first time that it has ever been reported, it would be a little surprising that this is the last thing that they could be used for.
So you already hinted a bit on it, but where do you see the main technological challenges currently in this area, like maybe related to scalability or, again, energy consumption, synchronization? Where do we stand here?
So yeah, so again, for the DCN, even though they popped the top off and put an OCS and made it spineless, the reconfiguration of those was very long. Okay, so that the topology and the time scale, the topology engineering is very long. Okay, and that was discussed in the Jupiter evolving paper. Similarly, for the when the OCSs are used in ML, they're basically configured during job time, during the model, and it's going to be set up. So again, the reconfiguration time of that, at least to date, plays a little bit in terms of how fast you can swap the cubes in and out, but it really doesn't impact this issue of do the transceivers have to switch more quickly or whatever. As we try to move, and if you will, try to chew off more topology engineering and try to make that topology engineering faster and faster, it's going to impact the technologies that we're going to need. And the first one, of course, is, as I said, the transceiver technology has to keep up in terms of its ability to be able to reacquire signals. And again, most transceiver technology is not designed to do this because it's designed to be turned on once and just stay there forever. So that's why Google actually had to develop, well, for other reasons, Google developed their own transceiver technology because they also took advantage of what's called bidirectionality and effectively doubled the number of ports. And that was an economic consideration. But as we try to make the functionality of the overall lightweight fabric higher, there are going to be challenges across the board. One is in transceiver technology, and in my opinion, the biggest challenge is going to be control plane, because one of the things that we learned, the hard way, was that it is very difficult to get a standard kernel to run quickly. And we tried to do kernel bypass, we tried to do all kinds of things. We tried to use priority flow control. We did many, many system level things. But at the end of the day, right now, the type of control plane that we're using with our rotor switch, which is switching at around 7 microseconds, is all hardware based.
Yeah.
You think it's going to be distributed control or centralized control?
Yeah, that's a great question. Well, okay. So demand oblivious doesn't necessarily preclude either centralized or decentralized control. However, the history of all networking is, centralized control only works to a certain level or to a certain speed, right? So SDN looked great for many, many years, but when people tried to really run, SDN over a bigger and bigger chunks and try to make it run faster and faster, that turns out to be problematic, right? And so the same issues that, it works great when you only need to change your topologies every day, right? But if you want to change your topologies on the time scale of a microsecond switch, you're going to have to do something else, right? And so at least with that UCSD, that's something else, is that we have spent a lot of effort developing our own FPGA-based NIC to handle the control plane, because and then to the question of whether it's centralized or decentralized, at a university, we can probably cheat a little bit because we can't build something large enough to show, right, that centralized control is going to be problematic. But I think the short answer is it's going to have to be decentralized at some point because it won't scale, right? So you can play around with centralized control over a limited set of nodes, right? But at some point, I think it's going to have to be decentralized to scale. I think that's a story that has been known in networking for many years.
Okay, good. I want to talk a bit about RotorNet. Mostly what you mentioned as example, I think most of them were demand aware, but you were involved in RotorNet. That was a pioneering solution that actually introduced demand oblivious reconfigurable network. Can you tell us a bit about maybe the key ideas in RotorNet and the technology of RotorNet?
Sure. I mean, RotorNet was a response to our inability to be able to do demand aware. So we did many, many attempts at trying to do demand aware for typical data center traffic, which means we had to do a collection, and then of course you had to actually get the traffic matrix. And then the biggest thing was that was not an insignificant time, and then factoring the traffic matrix into the set permutations using Birkhoff-von-Neumann, et cetera. So if you just look at all the steps that you need, and then look at the time, and then more importantly, look at how those times scale, none of those are nice numbers, okay? And at some point, it's the same statement I made before, that centralized scheduling just falls over, right? So then what can you do? So this was, I would argue, the genius of Joe Ford and Max Mellett, is that Max by this point had transitioned from doing a PhD with Joe to being a postdoc, and they understood that switching and routing can be decoupled. I think that is the biggest aha moment, is that what they effectively built, if I was talking to truly a physical layer people, was they built a gang switch. But so you had one element change the entire topology, as opposed to doing element by element changes, right? Which is how a typical crossbar would work. And in doing so, the speed at which you change the topology could be decoupled from the routes, okay? So really, if you wanted to call what RotorNet is, it's a topology switch. I mean, it literally is switching between topologies. That's by far the best way to understand it. We call those topologies matchings. And all a rotor switch does is the initial development was not necessarily periodic. So that was, I mean, we called it a rotor switch. You can go through a periodic sequence of matchings, but the initial idea is you just have a bunch of matchings that you can select. So that was the selector switch. And then later on, the rotor switches, which is what we are building now, is a specialized form of a selector switch where you cycle through these matchings in a periodic fashion. So there are two things there. It's the number of input-output connections for each of the matchings, and that has some very nice scaling properties, versus the number of matchings that you can actually access, okay? Rotor switches scale very nicely with the number of input-output connections. So Max and Joe have papers showing that a selector switch, they had physical optics designs for 2,000 ports. And the reason for that is these are just little points of light on an area. So if you can pack points of light densely on an area, and then you basically switch that area, you can keep scaling that, because what you have to do is increase the area. And that tends to be decoupled from how fast you can select those input-output configurations. And I think that was the key insight. And of course, it solved another problem, is we didn't think we could do centralized scheduling. So then the question becomes, well, what did you give up? And the short answer is, at any given time, you're not fully connected, right? And then that led to the second piece of the puzzle, which was Opera, which now, if you then have multiple rotors, and this, the key thing is the original idea of RotorNet did not necessarily say, I mean, I think we said we'd had multiple rotors, but we didn't say how those multiple rotors could be used to provide full connectivity in any time instant. So the key idea behind Opera, and again, that was Max and George and Alex Snoren, okay, to be clear, was at any instant of time, if you have multiple rotors, you can guarantee either a direct route, which is going straight through the optical switch, or an indirect route where the intermediate nodes can either store and forward, that was the original rotor LB protocol, or do cut through, which is Opera, which means you can immediately set the data through the intermediate node on a path. And then the other piece of secret sauce is, as you're probably aware, is that each one of those connection patterns that they cycle through is an expander graph. So, and we know it. So we can pre-calculate every single route from that we need. So if I'm sitting here at, switch 4, and I need to get to switch 8, I can have a direct connection. I'll use that all the time if it's there. But if I don't have a direct connection, then I can look and I could go through, node 4 to get there. And because each one of these are expander graphs, the probability of having a short path from any one node to another node is high, number one. And number two, they can be pre-calculated, okay? Because at any given time, we know what all 4 of the connection patterns are, and we know where they want to go. So we can basically say, go this direction and go through this intermediate node, okay? And that was the second key insight, is by using multiple rotors. We don't, so getting back to the question you say, we have to give up, latency with respect to switching. No, we don't. We can't, as if you've seen the Opera paper, we can't indirect everything because, there's this classic idea of bandwidth tax, is because just like load balancing, we're burning links to do this, right? So it's not free, but for latency sensitive traffic, if there isn't, a ton of it, it's actually very effective. Okay? And that was the second insight. Now there's all kinds of questions that come up, because now if you want to run rotor LB, which is store and forward, plus cut through, plus direct connections, that leads to a ton of system questions on how to organize everything. There will be contention at the intermediate nodes. Everyone knows this. This is a well-known problem in any kind of valiant load balancing system. But those are nice problems to have, because these are now system problems associated with protocol, in my opinion. The optics that can support it is there. Okay.
So you think that this oblivious topology is something that will be implemented in data centers?
Well, let's put it this way. I like to say academics is the art of the possible. You're going to be talking to a mean. A mean is the nuts and bolts of the practical. So those are the two different viewpoints you're going to get. I think that we're pretty far along in demonstrating at 128 ports. That switch is as big as the switches that Google's using in their data center. 7 microseconds is well over 1,000 times faster. But I think, in all honesty, someone's going to have to bite the bullet in terms of hardware control, right? I think that if you really want to take advantage of this, right? Currently, we run an unmodified Linux stack. All of the magic is occurring in the FPGA-based NIC, but there's a lot of magic that's going on there, right? And whether or not the benefit of trying to do that is going to justify the cost of being able to do this in some form of smart NIC. Whatever someone decides to do, I think that's an open question, right? If you're telling me right now, this is the greatest thing since sliced bread, I would say we don't know that yet. Because I think the system level questions of really how to implement this and making sure that we know how to handle congestion at the intermediate nodes, et cetera, all of those are going to have to get worked out. And I don't think, as I sit here speaking to you, I think, this is an active research topic, right? But it's an interesting research topic, and I think it does have potential to be beneficial. But like many research things, we're in a position where there's initial benefit, but to fully actualize that benefit, that's where the hard work's going to happen. And I think there's still a lot of hard work there to get these things to be a point where you can hand one off to a hyperscale and they say, oh yeah, this is great. And I really think, maybe I'm punting it to the other side of the fence, but I don't think it's an optics problem. I actually think it's a systems problem.
Okay.
Right. So actually, to conclude, let's even look a little bit further into the future. So do you see any future opportunities for this reconfigurable optical networks, maybe even beyond, rack-to-rack interconnector? So you also mentioned already with ROADMs and wide area networks. So
yeah, that's a fantastic question. So I think the answer is the same answer as what happened in interconnect. So, you know, first we could only use optics in the wide area network. Then we could use optics in the metro. Then we could use optics in local area networks. Then finally, the big push was when data centers came along and the data rate went above 10 gigabits per second, because at that point, copper cable couldn't go very far. So then optics interconnect, just, you know, transceivers were everywhere in data centers and will be everywhere forever, because they just go further at faster data rates. I think that that same kind of evolution is going to have to occur for switching, and I think it's just going to be a slower evolution path. So if you think about where we're using, or where Google's using it, right? They're using it at the highest level of the network, and they're reconfiguring these switches, even you know, in terms of topology management, extremely slowly, right? And as I said earlier, as we try to make these things run faster, we see benefit in trying to do that. But as we try to make the things run faster, there's these other ancillary issues, particularly with respect to control plane, like I mentioned before, that are going to have to be resolved, right? So really, the short answer is, from could we do it tomorrow? Absolutely. But how difficult is it going to be to build the control plane that can run at those kinds of, if you will, fast topology reconfigurations, right? Even if it's command oblivious. So yes, it's going to happen, but it never happens as fast as you want it to. And if you take a look at how just interconnect evolved, I think we're going to see a similar slow evolution of optical switching. And eventually, yes, I believe it'll be inside the rack for the same reasons that it's outside the rack now. But inside the rack, I don't think anyone's going to want to be doing reconfigurations on a minute time scale, right? They're going to want to be reconfiguring a lot faster. That has its own set of challenges. That's the thing. So that, you know, really, my story is, it's not just the physical optics. If we've learned anything, you know, in trying to build reasonably practical systems, is they have to be co-designed, and they have to be co-designed from the get-go. And as we try to make these things run faster and faster, more and more that co-design is probably going to be hardware, not software. And people don't like that, legitimately so, because it's not as flexible. So then you kind of bake in something that you might not want to bake in, and, you know, do you box yourself in terms of all the things that I complained about for electrical switches, which the next generation of data rate, you have to rip out your NIC or whatever. Yeah, all that stuff has to be worked out, right? But is there potential? Absolutely. And there's plenty of technologies that have been demonstrated that can work inside the rack. But it's all the other stuff that has to work along with it, which I think is going to be really the real issue.
Very interesting.
Great, George. I think we'll end with this positive note. Thank you very much for the interview and for sharing your thoughts. I learned a lot.
I think it's a great thing you're doing. It'll be very interesting, you know, my perspective versus Amin's perspective over the 20 years. But yeah, I mean, really, we absolutely need to have more physical optics people work tighter with the systems people, really, to evolve this, because if there's one thing that RotaNet has taught us, is that co-design really matters, right? Understanding both the physical optics and the system level challenges, getting those people together and getting them to work together, that's the only way we're going to move forward.
I totally agree.
So
thank you so much.
Thank you, and we'll see how that all turns out. Okay.
Okay.
Looking forward.
We'll update you. Don't worry. Thank you very much.
Okay. Yep. Hope to see both of you soon.
Bye. Thank you. Bye-bye.
Bye.